In 11.11, we look at Taylor polynomials. So Taylor polynomials are actually a simpler version of the Taylor series. So I believe I'm going to be able to do this section in one video, just one part. We'll see what happens. So the Taylor series, if you recall from our last discussion, is defined this way. The nth derivative of f evaluated at c over n factorial x minus c to the n, the summation from n equals 0 to infinity. And we did all that last time. So you remember the style. We always start by taking derivatives of our function and evaluating them at where we're centering to get those numerators. And then we kind of, we write all those terms out. We simplify them. Oftentimes we try and get the pattern, put it back into a series form as our final answer if we can. Okay, so what are we going to do here with the Taylor polynomials? A Taylor series has infinitely many terms. A Taylor polynomial has a finite number of terms. Okay, so in that sense, it's much simpler. We're going to define the Taylor polynomial of degree n. It has this notation, capital T sub n, Taylor of degree n of x. It is the Taylor series up to the nth term. The Taylor series up to n. Now remember, you start at 0, so if you go up to n, you actually have n plus 1 terms because of that 0 term at the beginning. Okay. So let's work through an example. This one is find T3. So that's the Taylor polynomial of degree 3. But because we start at 0, you're actually going to have 4 terms. We're just going to do one example here. Let's find T3 of x for f of x equals x natural log of x. Let's center at c equals 1. We are going to begin in the exact same way we did the Taylor series. Okay, so we're going to take that original function, evaluate it at c, 1, find out what we get. Well, that's 1 times 0, so here we get 0. All right, we're going to keep doing this until we get to the third degree, which is the third derivative. So we do the first derivative. Well, we would need a product rule. I won't bore you with the details. First derivative is natural log x plus 1. Evaluated at 1, 0 plus 1 is 1. Okay. We need the second derivative. Okay, 1 over x. Evaluated at 1, also 1. And because it's a t3, we need the third derivative. Negative 1 over x squared here. Evaluated at 1 is negative 1. And you can see, okay, yeah, there's 4 terms, yeah. Okay, that's it. We're going to stop right there. When you do a Taylor polynomial, doesn't matter what comes out as 0, what doesn't. We know where we need to stop. This is all we're going to do. We're going to use these 4 numbers. So when we go on, we're going to now use our same Taylor style. So we've got our first 0 there, 0 factorial, x minus 1, because that's where we're centering to the 0 power. We'll simplify that in a moment. The next one, hey, we've got the 1 over 1 factorial, x minus 1 to the first. Next one is also a 1 over 2 factorial, x minus 1 squared, and then a minus 1 over 3 factorial, x minus 1 to the third. Notice there's no dot, dot, dot here. We only want up to the third power, the third degree. Now all we're going to do is simplify our coefficients, and we got it. So that's, this whole thing is just 0. 1 times that, 1/2, 1/6, boom, there's T3. Done. Okay, so you may be asked to find, T4, T5. T3 is pretty popular, the third degree. Whatever your function is, wherever you're centering, that's what you're going to do. Take as many derivatives as you need, evaluate them, plug them in. There's no ... There's no pattern finding when you're done. It's just those terms only. Well, what else might be going on in this last section? Here, we take time to mention the Taylor remainder of degree n. And whenever you hear about a remainder or an error theorem, everyone cringes and says, "Oh no!" You take a simple concept and to find the remainder or the error involved compared to the infinitely long Taylor series. We've done this a couple times in the course already. It always really ups the difficulty, right? So we're going to call this capital R sub n, the remainder of the nth degree Taylor polynomial of x. If you thought about it, okay, so error we always think of as absolute value. We don't think of negative error. It's the difference between the original function and the nth degree Taylor polynomial. So that's going to be your error, right? How far off is one from the next? Even for values of x that converge, because we don't have infinitely many terms in our Taylor series, there's going to be some error, right? Okay. This we refer to as it leads to Taylor's inequality. So Taylor's inequality is really, really well known. This whole thing on the right side can be written as, well, we've got a less than or equal to. Our error is less than or equal to capital M over n plus 1 factorial over the absolute value of x minus c to the n plus 1. You notice a real similarity here to the error formula for the alternating series, right? You always take the very next term. So there's some numerator that's unknown, but then here it's the next value of n and the next value of n in the power, and we put that absolute value because we always think positive. Okay, Taylor's inequality. Very, very, very influential. Really, really big deal. The purpose in this class, though, we've done things with remainders. We get it. To use Taylor's inequality in this course would we'd be going beyond really what's helpful. So I have put a big X right through that whole thing. We are not going to use Taylor's inequality in this course. But I want you to know that it exists. I want you to know what it is and a little bit of the theory, just so if you see it in the future, you'll have a leg up versus people who maybe it's brand new to. Okay. If you get into some applied mathematics or applied, other realms like physics and things, you're definitely going to come across Taylor's inequality, and you'll use it there. But we don't need to do that in this course. But seeing it is really helpful. Okay, so what are we going to do? Instead, we're going to do this by graphing. We're able to graph Taylor polynomials. We're able to graph the original function. Here's what's going to happen. So you're going to see problems in the homework like this. We're going to find R3 of x, the remainder for the third degree Taylor polynomial for the function I'm about to show you. We're going to round it. We're going to use that same function that we worked with a moment ago. Okay. F of x equals x natural log of x centered at 1. And they're going to tell us boundaries of x. They're not going to give us the whole infinitely wide domain for the function. We're going to need some set boundaries. Okay, so here's what you do. If you were to find the remainder for the third degree Taylor polynomial, the first thing you would need is the third degree Taylor polynomial. Well, we did that a few minutes ago. So find the third degree Taylor polynomial, and this is what it came out as, right? Okay. Then we're gonna do this by graphing. So remember, this remainder absolute value, right? So the third degree remainder is the original function minus the Taylor polynomial, third degree Taylor polynomial, which we just found. We're going to graph that right there with the absolute values, and we are going to look for the biggest y value. We're looking at the differences, so we're going to find the biggest difference subject to our x values from 0.5 to 1.5. Okay, so we're going to use Desmos. This would be a lot easier in class. I'm going to grab the camera and show you my computer screen. Okay. I'm going to try and do it so that I can see what I'm filming at the same time, but that might not be possible. Okay, so I'm going to bring up my Desmos here, and hopefully how's it going? I haven't shaved in a couple days. Forgot about that before I aimed the camera at myself. Okay, so that's looking pretty good. What I've done, I don't know if you can see the color too well. In red here, that is the absolute value. So up at the top, I was able to graph y equals the absolute value, and I put in the original function minus big parentheses, put in the third degree Taylor polynomial, and absolute value. Okay, I also graphed vertical lines at x equals 0.5 and x equals 1.5. So this is what I'm looking at. Red line is the absolute value, but I only care what's happening between the two vertical lines. So I start to zoom in, and I notice that on the left, the gap is a little bit bigger than the right. Okay, so I want the biggest difference. I want the biggest error, right? So if this gap over here is larger, then I can ignore the one on the right. And I'm just going to zoom in here. And what's cool about Desmos, if I go back and highlight that red graph, it'll light up where these things cross. And I get at 0.5, the difference is 0.00759. Well, the problem, that's what I'm looking for. That's my value. That's my remainder. I'm going to round that to 4 decimal places and finish off this question. So back over here. There we go. The remainder there for the third degree Taylor polynomial to 4 decimal places, 0.0076. So you'll get several questions about Taylor remainder. Find that Taylor polynomial, graph it, just like I showed you. There you go. That is it for chapter 11. Homework is up. See you in the live session.